And now, Matthew Cameron is a consultant, trainer, business developer, translator, trade show manager, graphic designer, engineer, and biochemist.
Is that all?
Yeah. He's also been published in the Journal of Polymer Science with his paper, Fundamental Investigations into the Free Radical Copolymerization of N-phenylmalamide and norbornene.
Yeah. I read that in my book club. It was really good.
Yes. He's going to talk to us about a cool new technology to take CO2 out of the atmosphere and how science and innovation can help us take care of the Earth. Let's welcome Matthew Cameron.
Good morning, everyone. Thank you for the warm introduction. Glad to be here and very excited. So, just a bit about me. Obviously, they covered a bunch of the smart sciencey stuff, yada, 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 blah, blah, blah. But, I also do other fun things. Like, for example, I'm a Mickey Mouse voice impressionist. Oh, boy. Hi, everybody, watch out. Do you guys want to know what type of vehicle my girlfriend drives? It's a minivan. All right. Yeah. So, anyways, enough fun stuff, enough about me. Let's just hop right into it, all right? So what this paper was about and what the original investigation was into is we were seeking to reduce CO2 emissions from flue gases that were being burned by coal in order to create electricity, right? Now, flue gas itself isn't just carbon dioxide, obviously. As you're burning coal, you're going to have a lot of different elements that it's comprised of, but more often than not, the primary focus is going to be the carbon dioxide. So what we were hoping to search for was a thin polymer membrane that could select carbon, the carbon dioxide, but also let inert atmospheric pressures go through, such as nitrogen. So the reason why the entire process got started is in 2011, the EPA, Environmental Protection Agency, they reported 6.7 billion metric tons of carbon dioxide being put into the atmosphere. And, everybody's aware of what's going on with the greenhouse gases and things like that. And luckily, that's being continually brought to the forefront of our attention. So although there are multiple different techniques that are able to pull carbon dioxide from flue gases, the problem that's going to be behind a majority of them is that they require a phase change, a phase transfer, where the gas is being pulled out and the carbon dioxide that's inside of it is, they have to do what's called a phase change. So you change it from a gas to a liquid or to a solid, right? And anytime that you're shifting from gas to something else, it's going to require an intensive amount of energy. So that's skipping ahead just a little bit, a bit of a precursor, so that way you guys can be not, cyclo-dying from, anticipation. So, if you'd like, I can do the whole speech in Mickey Mouse's voice. I feel like some people, given the right crew, that could really work out, you know what I mean? So, but in 2014, the Clean Power Plan was introduced in order to reduce emissions nationwide by 30%. So, next slide, please. So as I already mentioned, the industrial gas separation exists in many different forms. Obviously, we're focusing on just the flue gas separation here. And then one of the tricky fun terms is we were looking for CO2 felicity, which is where it's the polymer itself was loving of the carbon dioxide. And there's a few different ways that you can go about this as you're developing the polymer, which is what the next slide goes into. So let's see. So what we have here is the selectivity as you're actually creating the polymer is going to be focused on, let's see. So we worked in collaboration with Oak Ridge National Laboratory, which is going to be inside of the United States, one of the largest research centers inside. So what we were looking at was something called the Robeson bound. This bound itself is where you're looking at the selectivity versus permeability of the nitrogen versus the carbon dioxide. So you can see up here that the Robeson bound, it has actually shifted from different time based on the development of polymers throughout time. So Robeson, who was one of the original geniuses behind it, and just to give a little bit of a background on polymer chemistry and the current research of macromolecules inside of its current state, is it's still relatively new in comparison to chemistry. You know, you think of chemistry, it's been around for forever, the elements, yada, yada, yada. But the development of macromolecules to actually selectively have the correct micrometer size to have the ability to collect carbon dioxide versus inert nitrogen is very new. It's on the forefront still of a lot of the technology. And even though this is a few years old, it's still something that's pushing forward. So what we had done in order to develop this membrane itself, and we'll go ahead and move on to the next slide, is we looked at different types of initial monomers, right? So what we were looking to do was, you see here norbornenes and cyclooctenes. So we did about 15 different types of initial monomers. And I know that this gets like a little technical, and jargony, so I try to keep it a little fun, but a bit of it's hard. So with the cyclooctenes, you know, this is the one where we did something called ring opening metathesis polymerization. It's called ROMP, and it's where it was actually a technically different way than what was generally accepted in order to make the polymers that we were creating. A lot of the polymers that were previously done, they weren't very high weight, they didn't keep complexity, and, you know, flue gas that's being burned from coal is going to be incredibly warm, incredibly hot. So we actually created polymers that were able to hold up of intensities of 360 degrees Celsius, which is significantly warm. So throughout each of these, you know, there were different techniques, different steps. You know, we followed lots of research looking at different macromolecules like articles and research and everything. And luckily, of course, this was a collaboration between the University of Tennessee's Polymer Department and Oak Ridge National Laboratory. So we got to have both sides of extremely, extremely intelligent people who have spent their lives trying to develop different polymer membranes like this. So if we'll move on to the next slide, please. So what we did was film preparation, right? This is going to be the actual creation of the polymer itself. Now, there's a lot of different steps that went into creating both the catalyst and the individual monomers, because what we did is we started with one initial monomer. And what you had seen on the previous screen is that there were different types of chains, and that's because we had different synthesis steps. While I was studying as an undergrad at the University of Tennessee, I took my senior year. I was extremely curious whether or not I wanted to be a graduate student. So I decided to spend the entire year doing undergrad research inside of the Polymer Lab, which is the only one at UT. And then I also spent the entire year doing just graduate study courses along with the capstone chemistry courses. I really enjoy investigating and diving in. And this gave such a unique opportunity in order to develop these films, and it's something that I looked at as I was going into that department as an undergrad. So, you know, if any of you have children, you know, which of course I'm sure some of you do, but, you know, I would really push and push and push for them to do undergraduate research while they're at university. It really is something that helped push me into an understanding that was so much more than just the undergraduate college level. But I digress. So from the film preparation, what we did is something called solution casting. So you can see on the left-hand picture here, you see a small little tray. So what we would do is we would prepare all the monomers. We would make them by hand inside of a glove box and everything. We would prepare the monomers by hand, create the catalyst by hand, because there were only, you know, a few different segments that were available, so we had to piece them together. Organic synthesis, organic chemistry, fun stuff. And, but so what the solution casting does is you create your monomer, you add your catalyst, but it's primarily inside of a solvent, which is just a liquid. We use something called tetrahydrofluoride, THF. And it naturally evaporates, leaving the monomer to, you know, just be wholly inside of the container without having any residual residue, because the evaporation rate of THF is much below room temperature, so it evaporates very, very quickly. And the polymers themselves that we were developing gave us, we were able to develop a high conversion rate and a heavy weight with about 5 to 10 minutes, which was very different. You know, a majority of the previous, if you wouldn't mind to go back to the previous slide, please. A majority of the previous iterations of developing these polymers was they had created very lightweight polymers that couldn't combine with itself, so the actual catalyst that we used was something significantly different. Previously, in order to do this polymerization technique, you would use a palladium MaO catalyst, whereas the new one that we had worked to develop with ORNL is a nickel antimony catalyst. So a bunch of fun words, of course, and but yeah, so those are going to be the differences there. Next slide, please. So that brings us from solution casting. So after the THF has had the opportunity to just evaporate, you have the polymer, which is left over. And then you can see in the center picture, it is actually a thin polymer membrane. But so then, of course, you think to yourself, well, how do you know what the thickness of that is? You know, how are you getting that so accurately? How is that reproducible? Well, we used a 45 micrometer syringe in order to put it inside of the mixture. But also, over time, we kept finding that we were inconsistently developing the film, right? You know, as we would measure it. So we started using what's called a doctor blade. This is where it just basically sets the height for you, and it does it on a thin glass layer, so that way you can get the exact micrometer film that you're looking for. And next one, please. So here's a bit of the jargon where you can see the testing analysis. Now, as you're, the next slide, if you don't mind to go to that one, sorry. The next slide, the testing and analysis. Here you can actually see the apparatus that we created at Oak Ridge in order to test the films that we were creating. So what we would do is that there would be 2 pressure chambers, and you only test for either carbon or nitrogen one at a time because you don't want to have a mix of the two. And all that it is that you have the gas that you're wanting to test on top, and then on this left-hand section here, you can see there's just the thin polymer goes right in the middle, and then there's a vacuum on the bottom with an electrode that can pick up the sensor and the amount of like carbon or nitrogen that's being pushed through. So we developed it ourselves, but of course it came from, you know, looking at other builds and things throughout time. So if you wouldn't go back, mind to go back just one. Thank you so much. From here, we can see the testing and analysis. So we're looking at permeance, which is going to be how quickly it can actually pass through. And then you multiply that by the thickness, that gives you the permeability. And then all you do is you put the permeability of carbon over the permeability of nitrogen, and that gives you your selectivity, which is A. And then forward a slide. One more, please. Perfect. So these were our results, right? The exciting part, what have we been waiting for? So what we were looking to do was get onto what's called the Robeson bound. The Robeson bound was created, I mentioned a bit earlier, where they had the original initial bound, which was from 1991, and then it pushed forward again, I think, in early 2000s, as people continued to develop the new macromolecular membranes. So you can actually see on the left-hand side, this is the most recent version of the bound. We come very, very close to it. And on the right-hand side, you can see all of the different polymers that have been created before ours that were initially trying to hit that same area. So the 4 red that you can see in the very center picture right there is going to be our polymer films that we were creating. So from there, I mean, that's what gave us such an initial inspiration and an initial push. And since then, we've actually gone on to develop another iteration of that first machine that I showed that actually does a higher level of testing. But what was so exceptional about being close to that bound and what provided the ACS macro publication was the fact that we were using a type of monomer that hadn't really been investigated yet. So we were pushing bounds of a certain molecule that just hadn't really been looked at yet, and its ability to have a high selectivity and a high permeability are, you know, one of the greatest aspects. So. Then next slide. Yeah, so gas permeability, right? Super interesting. It works really hard to capture all the CO2. Just one quick thing, since I've still got a few more minutes, is the iteration of the film itself. I haven't really talked about the applicability and how it actually gets put into the flue gas system, which isn't something I studied. It's more of the engineering side. But the applicability is that the best placement so far that's possible to be retrofitted is they have 90% reduction of CO2 from flue gas stacks. 50% of it is coming from a thin polymer membrane, as I discussed, that's similar to what we're currently doing and developing. So that 90%, it's a two-stage process, and that second stage is what sort of helps push it over the edge, but the second stage involves the phase transfer, as I had previously mentioned before. So as we continue to push in the realm of macromolecules, we're able to find more and more iterations of creating multiple polymers that are able to have better selectivity. And I really think as we continue to push, we're going to find more and more better results. So I do want to say a special thanks to the University of Tennessee and the Oak Ridge National Laboratory and all the team members that worked on this, because of course it wasn't just me. I was happy to be there, and I spent 10 months doing it. But there's all the references, of course, too. If you guys have any questions, the slides, I don't know if they'll be available online, but anyways. But yeah, feel free to check it out. If you guys have any questions, feel free to give me a question. And thank you all so much for your time. And yeah, do you have any questions? So sorry. Sure, yeah. Sure, so the applicability of it is there are flue gas stacks, you know, as you, so, yeah, where all the smoke comes out. So what we do is that smoke, as it's passing up, there's an area that gets vented over into a two-stage machine. The first stage of the machine passes over this thin polymer membrane, which selectively lets nitrogen pass through because that's good for the environment. It's inertly there. And the carbon dioxide is selectively captured because of this polymer. Right. Yep.
Wow.
Next time that will be the that'll be the title. That'll be the title. All right. Yeah. Go ahead. Right.
Getting filtered out. How does that carbon get removed? I mean, is it like a molecular furnace filter that gets clogged up and you have to change it every day?
Sure. No, I definitely understand. And the way that it works is they actually apply a set of air. So as it passes over, there's the film that's right here, right? They take a set of air that is clean from the boiler but heated. It passes across the top. And that movement of air actually helps the CO2 get pulled up into it to be recycled through the entire process again. And then also the portion that does get actually captured and grabbed from the film itself, you know, as it continues to cycle, parts of it get pulled down into the other phase transfer, like cryogenic distillation. So like basically they freeze it, and CO2 is a very reusable source inside of academia. So.
Interesting.
Yes.
Is there any possibility of somehow developing something that can take this film and collect that through the air and get rid of the CO2?
You know, I don't know of something like that just yet. I don't think that that's out of the realm of possibility, but usually in these type of situations, there's such an excess of CO2 that's being pumped out of these stacks. That's sort of what you need in order to capture it as much as it would be valued at. Yeah, oh yeah, no, for sure. I mean, if you could just, everybody take one, we all just do it together, we could sing songs and do it. I'd be great. I'd love it, like, I'm all for it, All right, yeah, I will work on that, I will. All right, well, thank you everyone so much for your time today. I really appreciate it. If you have any questions, please see me afterwards, and thank you so much.